Hi, this is me again, Sir Aris. Now let us talk about classification of differential equations. So one way in classifying differential equations is by specifying whether it is ordinary or partial. If the unknown function depends only on a single independent variable, we only have ordinary derivatives. So uh, our differential equation is an ordinary differential equation. So for example, if you have, we want to know the charge uh, as a function of time in a circuit where you have a capacitor, resistor, and inductor. This is the form of the equation, and this is an ordinary differential equation. On the other hand, if the unknown function depends on several independent variables, then we have partial derivatives, and it's called a partial differential equation. For example, the heat conduction equation or the wave equation, where here alpha and A are physical constants. So these two equations are partial differential equations. So in another case, we may have differential equations depending on a certain number of unknown functions. So if there are two or more unknown functions, we will need a system of equations. For example, the Lotka-Volterra equation given by these two differential equations. X and Y are populations of the prey, and this is end predator species respectively. A, alpha, C, and gamma are constants based on empirical observations and also dependent on the species. The order of the differential equation is also important. That is defined as the order of the highest derivative. So in our previous examples, they are uh, ordinary differential equations of first order. The LRC circuit is a second order equation. The heat and wave equations are second order partial differential equations. So in general, we can write an ordinary differential equation of nth order as this equation. So we express, this equation expresses the relation between the variable t, which is our independent variable, u, and the first n derivatives u prime, u first derivative, second derivative of u, and so on, up to n derivative. We can also write our function of u in terms of the independent variable t as y, so that the derivatives can be written as y prime, y double prime, up to y of corresponding to the nth derivative. So we can write our general equation as shown. If we have this example, y triple prime plus 2et times y double prime plus y times y prime equals t4 is a third order differential equation for y. Now, equations can also be described as either linear or nonlinear. If you have this differential equation, this is said to be linear if f is a linear function of the variables y prime, y double prime, y. So similar definition applies also to partial differential equations. So in general, we can write our linear ordinary differential equation of order n as this equation. So an equation not of this form is a nonlinear equation. So for example, LRC circuit heat wave equations are linear. The first is a linear ordinary differential equation. The second is linear partial differential equations. In the previous slide, I've mentioned about this example. This is not linear because there's a product of y and y prime. The Lotka-Volterra equations, they're not linear because of the product of x and y. If you have an oscillating pendulum with length L, angle theta, it would satisfy this equation. Second derivative of theta with respect to t, g over L, g is acceleration due to gravity, times sine theta. The sine theta doesn't make a linear function of theta, so this is a nonlinear equation. Now, in some cases, if the angle theta is small, then sine theta can be approximated as theta, so that the equation becomes d square, or second derivative of theta with respect to time, plus g over L theta equals 0. This is now a linear equation. And this process of approximating is called linearization. So generally, for a solution of ordinary differential equation given by this form, we rewrite the highest order yn in terms of a function of the other derivatives and the variable t. If the solution is given on this interval, alpha less than t, or t is between alpha and beta, it's a function of phi such that the derivatives of phi and phi exist and satisfy this equation for every t between alpha and beta. So we typically assume that the function is real valued, and we are interested in obtaining real valued solutions y equals phi t. Now, there are two questions that we want to ask when we are looking for a solution. That is, if there exists a solution, or that if the solutions that we get, or the solution that we get is unique. If the differential equations doesn't always have a solution, so to determine the existence, we will use theorems stating under which restrictions the equation will have a solution. If the differential equation has at least one solution, the next thing that we need to know is that we consider how many solutions and what additional conditions we must specify to single out a particular solution. So this is our issue on uniqueness.